the renewal process. So renewal process, if you look at some example like in Poisson process case, what is the Poisson process? It is again is a kind of the renewal. It is basically a particular example of the renewal process. So there that the inter-arrival times Tn we don't know. Tn is summation over I is equal to 1 to n tau of I, or that is called the time epoch. And where tau I, they are IID sequence of exponential random variables. So a specified distributions is given to you. Okay, but here the renewal, and then what is your NT? NT actually we try to find out that all those means supreme over n such that your S of n is less than equal to t, is it not? So that means it counts the number of jumps or the number of renewals up to times 0 to small t. Okay, that is NT you are denoting, and for particular distributions tau y which is exponentially distributed, and we call that process as a NT, that is a Poisson process. So here we'll look exactly similar else, but for arbitrary means IID. Okay, so basically what we try to find out the following, and look at the definitions. So now suppose maybe my notation is a little different. So T1, T2 and so on, say Tn, they are IID with distribution function say f. Okay, since they have the IID, they have the same distribution or the common distribution function f. Then I define S of n, okay, which is summation over I is equal to 1 to n t of I, and I define my S of 0 is equal to 0. Okay, so this Sn are the time epoch, you can say, at time n, and then I define my nt which is equal to suprema over n such that my S of n is less than equal to t. Okay, so for Poisson process case, this ti is nothing but the exponentially distributed with parameter lambda, is it not? So in that case f is known, but here it is arbitrary. We try to generalize that Poisson process case, that is again is kind of the renewal process, okay, to a abstract setup, and that is why we try to extract the main features from there and then we define in this way. So TIs, they are IID with distributions functions f, and Sn I am defining this time epoch S of n, which is the partial sum I is equal to 1 to n tau y, and with S0 is equal to 0. Then so this is basically NT is not what it says, that basically this is the number of, okay, so NT, it is the number of renewals up to time t. Okay, so supreme over n such that Sn is equal to this means number of renewals up to time t. So that is the renewal process, or the arrivals or the renewals up to time t. That is called the, this is called the renewal process. Sometimes this Sn is called the renewal sequences. Okay, so Sn is called the renewal sequences. So this NT, it represents the number of events that have occurred up to time t, or the renewals as renewals up to time t. Okay, so let us consider such kind of things happen or not. In particular, you know, Poisson process and Poisson process appeared in many real life examples. We have already discussed such kind of example. Now here I am considering another example. So suppose you have these light bulbs, okay, and then now suppose whenever some light bulb it burns, you immediately replace. Okay, so you have a tube light in your home, and then whenever it is burned, you immediately replace it. And now if I denote this Ti in that case, which is the lifetime or the life, random life of ith bulb, okay, with distribution function say capital F, okay, and then if I denote my NT, which is basically the number of bulbs replaced up to time t. If you think of NT, which is number of bulbs replaced up to time t. So then actually what will be your NT? You can think of NT is equal to your summation over n such that S of n is less than equal to t. That is the total number of bulbs replaced up to time t. So this example is basically called the repeated replacement of light bulbs. So this NT is a renewal process. Okay, so if you give a particular distribution shape, and from there actually we try to find out how the distributions of N2 looks like and so on, that is actually we will discuss one by one. Okay, so this is in real life example one can think of, since bulb is burning and you are immediately replacing that, and you can ask that, okay, what is the number of bulbs replacing up to time t? This is nothing but the renewal process, okay, NT, and your Sn is in this case summation over Ti. So if you look at these definitions from here, NT is equal to supreme over A such that Sn less equal to T. So from here actually I may have a relation that I can theorem. You can see directly that my NT is greater than or equal to K. Okay, if you have at least K number of renewals up to time 0 to t, this is same as that the epoch should be less than equal to t. That St should be less than equal to t. That means that kth renewals occur on or before t. That means Sk, which is less than equal to t. This just from your definitions, because what happened that Nt greater equal to k, if and only that the at least k renewals have occurred, and k renewals have occurred if and only that the kth renewal has occurred on or before the time 0 to t. So that means my NT greater equal to k, this is equal to Sk is less than equal to t. Okay. Okay. So now I try to find out what is the probability distributions of NT. So now you see that NT, it is basically taking the, like in Poisson process case, it's taking the non-negative integer value. So in this case also it is basically non-negative integer value. There is either no renewal or number 1, 2, 3 and so on. So I try to know what is my probability of NT is equal to K. Okay, so this is, I can write down, this is same as I can write down the probability of NT is greater than equal to K minus probability over NT, or maybe I put NT in this form. Okay, NT, this is greater than or equal to K plus 1. So then you have this part, the probability of NT is equal to K. And now this is by your this theorem, I can write down this is probability of, this is my Sk is less than equal to T. Okay, and then minus probability of S of K plus 1 is less than equal to T. So now if I denote my FKT, which is probability over Sk is equal to T, and this you can see this Fk is nothing but the kth convolutions or k times convolutions of your distributions F. Okay, so if you denote by Fkt, which is the probability distribution of Sk, Okay, the epoch random variable sk. So this is probably sk is equal to k. Then what I have less than or equal to t. Okay, this is the epoch thing. So then what I can write down, this is nothing but my fkt minus f of k plus 1 of t. So probability of nt is equal to k. I can write down this is fkt minus f of k plus 1 t. Okay. Okay, so here we will mainly interested in mt, which is the mean function. Okay, so sometimes it is called the renewal function. So the function mt, which is expectation of nt, okay, is called renewal function of the process with distribution f. Okay, basically later on we try to look at the asymptotic behavior. Okay, so what happened that mt by t as t goes to infinity, what happened, where it converges or not, is it not? So mt is now the real number, and not only that nt. So what you have seen there, that partial process case, that okay nt is finite almost surely and so on. So in this case also we try to find out that if you have a renewal process, so whether it is a finite almost surely or not, and so on. Okay, that I will come back to later. So whatever we try to, means whatever we know from the partial process case, because if you look at the definitions, it is nothing but the generalizations of that in an abstract setup, and we expect that similar kind of properties should hold here. Okay, but since it is a general kind of things, not all the property hold, but what are the essential properties there, it should hold here. Okay, in particular they say that nt should be finite, and then we try to know what happened my mt by t as limit t goes to infinity, that is the asymptotic behavior of the distributions and so on. Okay, so I can have in a different expression for my mt. So mt, this is nothing but expectation of nt, is it not? So now nt, this is a, for each t it is a random variable, not that it is a non-negative random variable, is it not? So now for non-negative random variable, you know from your probability course that expectation of x, if x is a non-negative random variable, then this is nothing but that if it is a non-negative random variable, then you can put as an integral form if it is a continuous setup, or if it is a discrete, then you can think of this is nothing but that probability of, means complementary distribution. If you look at probability of say x greater equal to k, and then summation over k is equal to 0 to infinity. So I am just trying to use that part, and then I am writing down this is nothing but summation over k is equal to 1 to infinity, probability over nt is greater than equal to k. Okay, so now this is summation over k is equal to 1 to infinity. What is my nt greater equal to k? We have already seen that it has a relation with my epoch, which is sk is less than equal to t. So this is nothing but the probability of sk is less than equal to t, and this is exactly by definitions of my fkt. This is summation over k is equal to 1 to infinity fk of t. Okay, is it not? Because sk is what? Sk is nothing but t1 plus t2 up to t of n. Okay, and then if you look at fkt, this is nothing but the convolution. You may heard about the convolution property of f. So this is convolution with n times. Okay, that I'll come back. So basically, if you have say two non-negative functions f and g, then I denote these convolutions, these things is by definition, this is 0 to infinity, say f of s g of t minus s d of s. And not only that, convolutions is basically commutes. That means f convolution g is same as g in convolution f, okay, at any point t. This is a convolution property. You just check yourself that these are the two things, okay. Okay. So this fkt is nothing but you can think of this is convolutions of f k times, okay. It is convolutions with k times. Okay, so this is the thing empty, but then question is from this definition sometimes it is not easy to compute this renewal function empty. Okay, so one thing you can check it from here, that I think you know the Laplace transform, no? For a non-negative say functions f, you know what is the Laplace transform. This is nothing but no, or L of x of any point t, this is e to the power minus t of x, no, expectation of. If x is a non-negative random variable, then Laplace transform of x is given by in this form, okay. Or in an integral form, if f is a function, is a non-negative function, so defined on 0 to infinity, okay, to a real number, then the Laplace transforms L of f, it is denoted by what I can write down, integral over 0 to infinity e to the power minus sx f of s of dt. Sorry, s minus t. Sorry, e to the power minus what I am writing down, L of f I am considering, no. So e to the power minus s of t f of t of dt, okay. If I put as a value s acting at point s, then it is nothing but x, and this is actually you can just replace it using this form, okay. If your f has a density function, then this f is nothing but the density functions, and then you are having exactly this part. So good property that if you have a convolutions, so suppose I have a convolutions of two functions f and g, and then if you look at the Laplace transforms at time t, then this is nothing but the look at the Laplace transforms and then product by g of t, okay. You can check yours, so this is nothing special, it is a simple thing. Just one needs to use that Fubini theorem, means there is some kind of, you need to interchange the two limits and so on, iterative type of integral, and from there actually you will find out. Okay, so why I am saying this Laplace transform, actually this MT I can think of in terms of Laplace transform, because suppose your f, which is a distribution function, okay, is given to you, and fk is nothing but the k times distributions, and then if you apply this form, then from here actually whatever I have, now this is summation over k is equal to 1, means if you look at the Laplace transform here, so L I am just denoting as m at point t, which is the Laplace transforms of my m, then this is nothing but summation over k is equal to 1 to infinity, then fkt, and fkt is nothing but that convolutions k times. So if you denote that L of say f, which is the Laplace transform, then you have your Lf to the power k form. And now this Lfk, since your f is a distribution function, you check that it is lying between 0 to 1, hence this sum is nothing but 1 by 1 minus L of f, is it not? Because of these things it converges to here. So, and then your L of f is equal to there, and then you try to look at the inverse transform, inverse Laplace transform, then you will get the m. Okay, sometimes one can use this thing to find out the renewal function m. Is it not? So I have Lm of t is equal to 1 by 1 minus L of f. Okay. So now if you look at the inverse Laplace transforms of that, then you have mt, which is nothing but L inverse of this is whatever we have 1 minus 1 by L of f. Okay. And from there, if you know these things and this part, and if you know the inverse transform, Laplace transforms of that, then you can find out mt. Sometimes this may useful for some particular example. Okay, so here I try to give you a integral form or the integral equations which satisfies my mean or the renewal function mt, that I am writing down in terms of lemma. So let mt, this is the renewal function of the renewal process, say nt, okay, with distributions function, or sometimes called the duration of life distribution. Say f. Then mt satisfies the following equation. So mt, this is my ft plus 0 to t m of t minus x dfx. Okay, this is the Riemann Stieltjes integral, or as I told you, it's you can think of something like distribution, the convolutions of m with respect to the distribution f. Okay, so this equation is called the renewal equation. This equation is called the renewal equation. Okay, so mt you can find out using the Laplace transform, as I told, or one can use also the renewal equation, which says that the renewal function mt of a renewal process satisfies this integral form. That means mt is equal to ft plus 0 to t m of t minus x dfx. Okay, sometimes this is m is equal to f plus m convolutions f. Okay, in a simple notation, this is the case, because this is the nothing but the convolutions of f with m. Okay, how to prove it? Let us try to prove it. So t1, which is the first renewal time. Now if you try to take the conditional with respect to my first renewal time t1, then we'll see what happens. So I can write down my mt. These things is nothing but expectation of nt, is it not? And this one I can write down by using the properties of conditional expectation, that expectation over nt given t1, and then you take that expectation, is it not? So now this is nothing but, by definition, I can write down this is 0 to infinity expectation of nt given t1 is equal to x. Okay, and then I have d of fx. Okay, so now you consider, so given x is greater than t, so if x greater than t, now if given my t1 is equal to x, which is greater than t, that means what? That there is no renewal. So this implies there is no renewal occurs in 0 to t. Is it not? Because t1 is equal to x, which is greater than t, that is the first time. That means in between 0 to t, there is no renewal. No, because t1, this is the renewal time. No, Sn you have that epoch, and then t1 plus t2 plus t3 and Sn is equal to summation over that part. So now t1 is equal to x, which is greater than t. That means in between 0 to t, there is no renewal occurs, and hence expectation of nt given t1 is equal to x, that is actually 0. This implies expectation of nt given t1 is equal to x, this is 0. So now consider the other option. That means 0 should less equal to t. Okay, so here actually my capital T, whenever we are looking for the stochastic process, that the time parameter here is t greater equal to 0, or the r plus actually we are looking for, because that is the evolution things in real life it is required. So for x is greater than t, then we have seen that if you look at the conditionals with respect to t1, the first initial time, then this happen. So now 0 less equal to x less equal to t, and if my t1 is equal to x, that means that first renewal occurs at x, then the process starts at time x, and then the expected number of renewals in the remaining interval, which is length of t minus x, because total is 0 to t, and we know that at time x, where x is less than equal to t, the first renewal occurs. Is it not? So that the mean or the expected number of renewals in the interval, the remaining interval, that is basically expectation of m of t minus x. Is it not? So what I can have, that expected value of nt given t1 is equal to x. In this case, this is what, but at x first renewal happen, and then the what is the other thing? Other is nothing but expectation over n of t minus x, which is nothing but 1 plus m of t minus x by your definitions of m. So what I have, if you combine from here, in this case, this is the empty thing actually I am writing down. So empty, then effective things should be, it is 0 to t. So this is 0 to t, expectation over nt given t1 is equal to x, and then df of x. These things actually I can write down 0 to t. This is nothing but 1 plus m of t minus x d of fx, and this is nothing but, if you just do these things, ft plus 0 to t m of t minus x d of fx. Okay, that is actually we want to show. So the renewal function mt, it satisfies the following renewal equations. Mt is equal to f of t plus 0 to t m of t minus x d of fx. Okay, let us consider one example where we can compute the renewal functions. So this is the integral equation. Sometimes one can use this integral equation to find mt. Sometimes, as I told, using the Laplace transform, one can find out easily. Okay, it is depending on the problem. Okay. So for the example, I am considering the renewal process. Nt with distributions f which is uniform between 0 to 1. That means I can write down the density functions, which is 1 if 0 less equal to less than equal to 1, and 0 otherwise, is it not? So if the distributions f has a density function, or that ti's, which is the interval times, if they have the density functions, then actually you can write down, no, this is nothing but your f of x d of x, is it not? In this case you can have. So in this case, from the renewal equations, what I have, mt, which is equal to t plus 0 to t. Okay, what I have, this is f of x d of x, and then only for 0 to t it happened, this is m of t minus x dx. So whenever t is lies between 0 to 1, is it not? So t is lies between 0 to 1, I am having mt. So this is again the integral form, but if you look at it, is in a linear type of thing, so I can differentiate both sides, so that m prime t, okay, because you see that here it is differentiable and so on, m prime t, I can have this is 1 plus m of t, is it not? So in this case, if you look at ht is equal to, if you take ht, which is equal to 1 plus mt, then m prime t is equal to h prime t, and then whatever you have h prime t is equal to h of t. And from these equations I know the solution, because this is a first order linear differential equation, and I know that solution ht should be some k times e to the power t. Okay, so now m of 0 is equal to 0. Now at t is equal to 0 and 0 equal to 0, so that mean should be 0, and from here I have h of t is equal to e to the power t minus 1. Okay, because k is equal to 1, I have, sorry, this is not ht, k is equal to 1, so e to the power t, and hence what I have, that m of t is equal to e to the power t minus 1 for all 0 is equal to t is equal to 1. So the renewal functions for this is given by in this form. Okay, for this example. Okay, so as I told you that what happened, or the asymptotic behavior we try to find out, that what happened as t goes to infinity of nt, whether that is finite or not. So what we have seen, that for each finite t, nt is finite, is it not? That is again by how we construct it, because whenever your small t is finite, you are looking for the number of the interval times, or the number of renewals, or the number of events occur in between 0 to small t. So there it is finite. But I am saying that what happens as t goes to infinity. So asymptotic behavior. So for that case, you can expect that it should be infinite. But since it is a random variable, you have to say that okay, it is almost sure sense, or in which sense, is it not? Because it is kind of the convergence you are looking for. Since it is a random variable, so you have to specify which convergence. That I am giving in this theorem. So let nt be a renewal process, then probability of limit t goes to infinity, nt is equal to infinity, that is actually is equal to 1. That means limit t goes to infinity when t is equal to nt is equal to infinity with probability 1. That is actually we try to show, prove. Okay, so how I can show? A1, this is limit t goes to infinity fn t, is it not? So for all n greater or equal to 1, I have these things f and t, because this is the distributions function. Distributions functions, I know that as t goes to infinity, that f of x as x goes to infinity, f of x is equal to 1. So I have for each n that 1, which is limit t goes to infinity f and t, is it not? Because fn is nothing but the distributions of your Sn, and this is nothing but limit t goes to infinity probability over Sn is less than equal to t, because f and t is nothing but the probability of Sn less than equal to t. And because I want in terms of my nt, so already I know that what is the relation between nt and my f of Sn. So this is nothing but limit t goes to infinity probability of nt is greater than or equal to n. Okay. So now suppose, and then this is nothing but probability of limit t goes to infinity and t is greater than or equal to n. Why this is so? This is nothing but the continuity property of your probability. It is not the continuity property. What I am kind of saying that, no, you know that if suppose you have your a1, a2, a3, all these are decreasing sequence of events, and then if you look at the union, okay, or the intersections, that and that limit actually it gives you same as your union of an. That means if you look at that limit in this case, I can interchange limit and probability. Okay, that is the properties of your probability p. I am just looking for, because nt is greater or equal to n. Okay, n is fixed. Now if you allow more t and so on, that means that omega, that is actually increasing. So now that limit actually you are seeing, that means actually you are looking for that lim sup of that an, which is actually you can look at the union, and that is nothing but that limit t goes to infinity nt, which is greater or equal to n. Okay, that is the properties of your probability. I am just using here. So that means what? For each n, what I am having probability of t goes to infinity n t greater or equal to n, this is actually is equal to n. So that means by definition that limit, this implies that probability of limit t goes to infinity of nt is equal to infinity. This is actually your, no. So if you just start with these things, what does that mean? Probability of limit t nt is equal to infinity. That means actually I can find, any things there exist these are that you can always find better. That means if I write down that for each n, if I am able to show that probability of limit t goes to infinity nt greater or equal to n is equal to 1, that means that probability of limit t goes to infinity nt is equal to 1, which is equal to 1. Okay. So now we want to understand, or we want to know in which rate actually it converges. So for that I have the following theorem, because see nt goes to infinity as t goes to infinity with probability 1. That is actually we have from this theorem. But we want to know in which rate actually it converges to infinity. So it is given by this theorem. Because already in the Poisson process case you have seen, no, nt by t, that is converges to 1 by mu, which is basically lambda, in that case 1 by mu, because mu is the expectations of your the interval times. So nt by t that converges to lambda as t goes to infinity. So the theorem is the following, exactly similar kind of things actually I had with probability 1 nt, which is the renewal process, nt by t, this converges to 1 by mu as t goes to infinity. What is my mu? Mu is nothing but expectation of T1, because Ti is the IID, so T1, T2, expectation of T1 same as expectation of T2 and so on. Okay, let us prove it. So for that, actually, one can use simple strong law of large numbers. So what is strong law of large number? If you know that if you have a IID sequence, okay, then the average Sn by n, okay, sample average Sn by n, or xn bar, actually sometimes you wrote down xn bar is equal to 1 by n, summation over I is equal to 1 to n x of I. If xi is a IID sequence with mean finite, mean and variance, then that converges to mu with probability 1. Is it not? That is a strong law of large number. So here actually we try to use that strong law of large number and then the previous property to find out whether my nt by t, it converges 1 by mu with probability 1 or not as t goes to infinity. Okay, so now for any t is positive, already we know that nt is equal to n. This is if and only if Sn, this should be less than equal to t less than s of n plus 1, is it not? Because if it is less than equal to t, then I should count that nt should be n plus 1. So the Sn, which is the epoch at time t less than equal to t, and it should be less than s of n plus 1, because I am just trying to count the renewals, no, the number of renewals occur between 0 to t. So now nt is equal to means only exactly n number of renewals is happening. That means my Sn should be less than equal to t, and this is strictly less than s of n plus 1, is it not? Because if it is equal to, then actually I should count that then nt should be n plus 1. So this is the if and only conditions, that nt is equal to n such that this happen. Hence I can write down s of, if you replace, because n is equal to nt, so I have this s of nt by nt, this is less than equal to t by nt, okay, this is less than s of nt plus 1 by nt. I can just write down from here to here. So now this part actually I try to write down s of nt plus 1 by nt plus 1, and then I can write down nt plus 1 by nt. Is it not? Okay. So now s of n, what is your s of n? S of n is summation over I is equal to 1 to n of my t of I, and ti, they are IID with mu is equal to expectation of t1, which is finite. Is it not? So by strong law of large number, in short I put SLLN. Okay, so you can, if you don't remember the strong law of large number, I already state the statement of strong law of large number, but for its proof maybe you can look at any standard probability book, but it is, I think, from your probability course already you have seen it. Okay, strong law of large number. So then what I have, that Sn by n, okay, this converges to mu with probability 1. This part I know. So now already I have seen that as t goes to infinity, nt that converges to infinity with probability 1. Hence s of nt by nt, this converges to mu as t goes to infinity with probability 1. Okay, is it not? So thus if you look at from my here, because this converges Snt by nt, you have this part, so now you have your 1 plus nt converges to infinity, so 1 by nt this converges to 0, so that means here actually I can have that limit t goes to infinity t by nt. Okay, this is converges to, because this is converges to mu. Now since mu is non-zero, I know that if xn converges to x, where x is greater than or equal to 0, is still greater than 0, then 1 by xn converges to 1 by x almost surely. So this implies, using my previous thing, I can say that limit t goes to infinity nt by t, this is converges to 1 by mu. Okay, or equal to, maybe I can write down, with probability 1. Is it not? So here actually we are using strong law of large number, and my previous theorem that as t goes to infinity, nt converges to infinity with probability 1. Okay, and then another thing is that if xn converges to x, almost surely for x is strictly positive, then 1 by xn, okay, 1 by xn, this is converges to 1 by x almost surely, and all together using this relation that there exists, means if there exist n, only exactly n number of renewals, if and only if Sn less than equal to t less than s of n plus 1, from there we deduce that limit t goes to infinity nt by t is equal to 1 by mu with probability 1. Okay, let's consider one example. Already you have seen that, like in Poisson process case. So nt, now the Poisson process. So now nt actually it's a renewal process with distributions functions f is okay, Poisson process with rate lambda or intensity, okay, with rate lambda. So then this f is nothing but the exponential distributions with parameter lambda, and in that case what I know that mu is equal to 1 by lambda, is it not? Expectation of ti in that case, that is equal to 1 by lambda. So then my previous theorem I can say that nt by t, this is converges to 1 by mu, which is equal to lambda as t goes to infinity with probability 1. Okay, for Poisson process case I know the interval times and hence the duration of distribution function f, which is exponential distributed parameter lambda, and from there using the previous theorem I have this. Okay, so this theorem what it says that the number of renewals per unit time converges to 1 by mu, is it not? So for large t, because this is the limit as t goes to infinity, so I can say that for large t and for unit time, that number of renewals per unit, it converges to 1 by mu. So then our next goal is, what is the expected number of renewals per unit time as my t goes to infinity, means asymptotically what is the expected number of renewals. So this is given by the following theorem. Sometimes this is called the elementary renewal theorem. Okay, what it says that if you have a renewal process nt and my mt, which is the renewal functions, means expectation of nt, then mt by t, which converges to 1 by mu as t goes to infinity. So now mt, this is a real number, no? So convergence means basically it is a real number sense. Mt is a real number. because it is expectation of nt, so expected number of renewals at time t. So then actually we are looking for asymptotic times. So this theorem says that again for t large, that the expected number of renewals per unit time is nothing but the 1 by mu. Is it not? It converges to 1 by mu. That means approximations is 1 by mu. Expected number of renewals per unit time for t large enough, because t goes to infinity. So in real sense, for t large enough, mt, which is small mt, means expectation of nt, expected number of renewals per unit time is 1 by mu, where mu is the expected value of the interval times t i's. Okay. So to prove that things, actually we need some preliminaries that I'll come back. So today I try to prove this theorem. Okay, so for that I need some preliminaries. Okay, so let us recall the stopping times. So what is the stopping times? So we say that n, which is a function from omega to 0, 1, 2, 3 and so on. That means it is a integer value, non-negative integer value random variable, and it's called a stopping time. Okay. If the following holds, n is equal to small n, okay, n is equal to small n, this is independent of the random variable x of n plus 1, x of n plus 2 and so on. Okay, 1, 2, 3 and so on. So I am looking for n is a stopping time with respect to my sequence xn. If n is equal to n, this is the event, it is independent of the random variable xn plus 1, xn plus 2 and so on. For example, suppose you cos a toy, okay, and yi, which denotes the outcome of the ith toss. Now you define xi, which is equal to 1 if your ith head occurs. It means xi if in the ith outcome head occurs, and 0 if tail occurs in the ith toss. Okay, so yi, which is the outcome of the ith toss, and I define my xi. So now what is my p? I am considering p, which is my probability of x of I is equal to 1. This is the p. So then what is the expected value of xi? This is nothing but again p. Okay. So now what is my Sn if I denote summation over I is equal to 1 to n of xi? So then this Sn is nothing but the number of heads in the first n trials. So Sn denotes number of heads in the first n tosses. Is it not? Cumulative number of these things. So now I am defining my random variable, which is non-negative integer value random variable, and this is minimum of all those n such that my Sn is equal to m. So now you see that Sn is equal to m. This set, all those omega Sn is equal to m, it does not depend on your that x n plus 1, x n plus 2 and so on, because Sn, which is summation over I is equal to 1 to n xi, it only depends on a first n trials. Is it not? It does not depend on the others xn plus 1. Hence my n is a stopping time with respect to my exercise. Okay, so I need this stopping time conditions or the stopping time notion to prove my elementary renewal theorem. We'll see that how it will come. So basically, from where this stopping terms comes into picture, so my claim is nt plus 1. What is your nt? Nt is the renewal process. Then nt plus 1 is a stopping time for the sequence ti, which is the interval times. How to prove it? Because later on actually I need. So in particular, what happened actually, that we have seen, no, if you have say xi and say I is equal to 1 to some n, okay, if n is your random variable and xi's are independent of n, so for that case I know that this is expectation of n and then expectation over xi. So then question is, what happens if n is your stopping time? So whether I can have the similar kind of expressions or not, and so on. So that is given by the Walsh theorem. So basically it is true even if you replaced by stopping time. Okay. So that is we'll see little later, but first we should prove it that nt plus 1, it is a stopping time for the sequence ti, not only nt plus 1. How to prove it? So my nt plus 1 is equal to n. This implies what? This implies my s of n minus 1, it should be less than or is equal to t, but s of n, it should be greater than or is equal to t. Then actually it is happen, n2 plus 1 is equal to n. Is it not? So thus the event nt plus 1 is equal to n, it's only is independent of tn plus 1, tn plus 2, and so on. Okay, so thus nt plus 1 is a stopping time. Is it not? Because Sn minus 1 and then Sn, it depends only on the Sn greater than T. So, but Sn is nothing but summation of I is equal to 1 to Ti. Okay, and Ti's are the independent. Is it not? So that is why this event nt plus 1 is equal to n, it is independent of the sequence tn plus 1, tn plus 2 means interval times tn plus 1, tn 2, and by definition nt plus 1 is a stopping time. Okay. Okay. So as I said that I want to know this case, that if you have a random variable which is independent of each exercise, and suppose xir iid, so then I know that this is means you can just look at the conditional with respect to n, and then you find out exactly this part, expectation of n times expectation of xi or x of 1, because they are same. So now question is, what happened that if n is a stopping time for the sequence xi. So this theorem, and as I told, that same result will hold, and that theorem is called the Walsh theorem. Maybe you are familiar with that, I don't know, but I try to write down. what it says that, so let xi there be sequence of independent random variables with same expectation and let n be a stopping time for xi such that expectation of n is finite. So then expected value of summation over I is equal to 1 to n xi, this is same as expectation over x1 expectation over n. So this result holds for stopping time. Okay, I'll prove little later or maybe the next class. I try to prove it the elementary renewal theorems, and for that I'll use Waltz theorem. Okay, so proof of elementary renewal theorem. So what I have to prove? I have to prove mt by t that converges to 1 by mu as t goes to infinity. Is it not? And expectation of s of nt plus 1. This part I can write down. This is nothing but expectation of summation over I is equal to 1 to nt plus 1 of ti. This is by definitions of Sn, which is the epoch. Now nt plus 1 is a stopping time with respect to the sequence ti's, that we have proved it, is it not? And hence by Waltz theorem I can write down this is nothing but expected value of nt plus 1 times expectation of t1 or t of I, and this is nothing but expectation of ti is mu, this is mu times, and this part is nothing but 1 plus mt, is it not? So from here what I can write down, so this implies mt by t. From here actually what I can write down, if you multiply it by means divided by t, so then I have this is nothing but 1 by mu t expectation over s of nt plus 1 and minus 1 by t, is it not? Just because you divided by mu and then you divided by t, so 1 by t you take the left hand side, so it should be 1 by t. This part I have. So now these things actually I can write down. This is 1 by mu t expected value of s of nt plus 1 minus t minus 1 by t plus 1 by mu, is it not? Because from here what I have 1 by mu minus 1 by mu, that is why I add and subtract 1 by mu. Okay, so now s of nt plus 1, this is greater than t, is it not? S of nt plus 1, this is always greater than t, because nt, which is the number of renewals up to time 0 to t, so s of nt plus 1, that should be always greater than t. So this implies that expected value is positive. So expected value of s of nt plus 1 minus t, this is greater than 0, because already we know that if x is a random variable, a non-negative random variable, then expected value is non-negative. X greater or equal to 0 implies expectation over x is greater or equal to 0. Okay. So from there, it's kind of the monotonicity property of your expectation. From here, actually, what I can have, so now this part is positive. Okay. So from here, actually, what I can write down, and 1 by t I have. So now if you look at that lim inf, so this implies lim inf of as t goes to infinity mt by t, this should be greater than or equal to 1 by mu. Is it not? Because this one is positive, so that means basically this is 1 by mu minus 1 by t and so on. Now if you look at the limit, that should be 1 by these things. So I denote as t. So what is left? If I try to show that mt by t as t goes to infinity is equal to 1 by mu, I try to show that, so maybe m, if I show that lim sup over t is infinity mt by t, this is less than or equal to 1 by mu. Okay. So then combining my 1 and 2, I can say that mt by t as limit t goes to infinity is equal to 1 by mu. So this one we usually got it, that 1 by mu is less than or equal to lim inf of mt by t. So I try to show the second inequality. Okay, so for that I need two things. So case 1, now suppose my ti's, that interval times, ti is bounded. Okay, so ti is uniformly bounded. What does that mean? That means that is there exists some m positive such that probability of t of n is less than or equal to n. This is 1. This holds for all n. Okay, I can find a fixed m such that Tn is less than or equal to m, probability almost surely. This is the meaning that it is uniformly bounded, and this holds for all n greater than or equal to 1. So thus I can write down that expectation of t of nt plus 1, this is always less than or equal to m. Is it not? This I can have, this is less than or equal to m. Okay, check yourself. This is simple. So now what I know? What I know that s of nt plus 1 minus t, this is less than or equal to s of nt plus 1 minus s of nt, because of that part s of nt I have. So now this part is nothing but my t of nt plus 1. This part s of nt plus 1 minus s of nt. So if you write down, because Sn is the partial sum over ti's, so from there you have s of nt plus 1 minus s of nt, this same as t of nt plus 1. So now from my previous expression what I have, mt by t, this is less or equal to 1 by mu t expected value of s of nt plus 1 minus t plus 1 by mu, and these things is equal to 1 by mu t, and then what I have, expectation of nt plus 1 minus t, this is less than equal to t of nt. So this is expected value of t of nt plus 1 plus 1 by mu. So now these things is less than, because expectation of nt plus 1 less than or equal to m. So this is m by mu t plus 1 by mu. Is it no? So this implies that lim of sup as t goes to infinity. This implies lim sup of t goes to infinity, mt by t, this is less than equal to 1 by mu. Okay, and hence for t uniformly bounded case, we have proved that elementary renewal theorem. That means limit t goes to infinity, mt by t is equal to 1 by mu. Is it not? So this is for case 1. So this implies limit t goes to infinity, mt by t is equal to 1 by mu. Okay, maybe I can say combining 1 and 2. So this is for whenever t is uniformly bounded. And the second question is, if t is not uniformly bounded, then we try to, these are the natural way to do that, you consider the truncation. Okay, that means whenever truncation error is finite, is for fixed truncation k, then I have this truncated interval times, they are uniformly bounded, and from there I can have exactly something else. Okay, and then we try to show that as k goes to, or the truncation parameter, it goes to infinity, it will converge to the right direction. Let's see. So case 2, the ti not bounded. So I fix k is positive and define tnk, which is tn if my tn is less than equal to k, but there are many cases because tn is not bounded, so I can consider my k if tn is strictly greater than k. So now we see that t and k is uniformly bounded by k. Is it not? So this implies my t and k is uniformly bounded by k, because the parameter now here n, k is fixed. Okay, for each fixed k, I am looking for the interval times t and k, which is defined in this form. So now it is clear that t and k, they are monotonically increasing, no? So t and k, it converges monotonically to my tn. Is it not? So as k goes to infinity, this is just like, this is called the truncation. Okay, this is a natural way to do these things. So even I don't know whether you have heard about these things. So whenever you have say differential equations, and what we know that in particular, if you have a say non-Lipschitz coefficient, okay, so there you cannot apply existence and uniqueness. In particular, uniqueness, existence is possible, but uniqueness is not possible. So in that case, general idea is okay, you consider the truncation, so that you consider the approximations where the approximate function is Lipschitz continuous and it converges to your given functions in certain sense. So now you look at that as a parameter, you look at the different kind of differential equation there, and there you can apply your existence uniqueness theorem. So you have a solutions there, and then you try to pass to the limit as your parameter k, the truncated parameter k, converges to infinity. Okay, so it may not be possible for all problem, but most of the cases this is the natural way to do that things. So here also we are doing the similar kind of things, that if ti are uniformly bounded, then we have proved these things in a easy way. But then question is, what happens if it is not bounded? So we try to look at the truncated interval times tn, and this t and k, this converges to, basically increasingly converges to tn as k goes to infinity. So now I can consider the renewal process. With respect to this T and K, which I denote as NTK. Okay. NTK, this is again the renewal process with the interval times. Now T and K. Okay. So according to case 1, what I know, that limit T goes to infinity, MKT, okay, I will write down what is MKT by T, this is equal to 1 by or less than equal to 1 by expected of T1K. Is it not? Because mu, initially we have mu, which is mu is equal to expectation of T1. So in this case, this is T1K. And what is my MK of T? This is nothing but expected value of my renewal function NTK. Is it not? So now observe that SNK, which is nothing but summation over I is equal to 1 to n Ti over K, this is less than or is equal to my Sn. Is it not? Just looking for my truncation things here, it is exactly nothing but is equal to S of n, and hence what I can have, that M, which is, see, whenever Sn t less than equal to Sn, the associated renewal function, it should be in a reverse way, no? Because we know that Sn t less than equal to Sn less than equal to t, which is same as my n of t greater than equal to k. Is it not? So in a reverse way, that means I have my mt, this should be less than equal to mk of t. Okay, and hence I can find out that lim sup over mt by t, t goes to infinity, this is less than or equal to lim sup of mkt by t, which is nothing but 1 by, that is we have seen just here. Okay, this is 1 by t1 of k. So now what I know, that T and K, this converges increasingly to T of n. So now if you apply the monotone convergence theorem, that expectation of T and K, this is converges to expectation of T of n, which is equal to mu as K goes to infinity. So that means I can say, so this implies that lim sup over mt by t, because I can take again limit k goes to infinity, so this is independent of k, so this is less than equal to 1 by mu. Okay, so monotone convergence theorem, maybe you have heard about this monotone convergence theorem. What it says that, so suppose my xn, okay, converges to x almost surely monotonically, okay, or if xn is monotone, suppose xn is non-negative, xn converges to x almost surely, then I can interchange the limit and expectation. So that is why the monotone convergence theorem says. So xn is positive, xn is increasing to x almost surely. This implies that expectation over xn, or limit n goes to these things, is equal to expectation over x. Okay, this is the monotone convergence theorem. So there are three important convergence theorem, maybe you have heard about. One is called the dominant convergence theorem, maybe I just state it. So what it says that, suppose I have a sequence of random variable xn such that xn converges to x almost surely, and there exists a y such that xn is less than or equal to y, okay, and my y is integrable. That is the notation, y is integrable. That means expectation of mod y, this is finite. Then I can interchange the limited integration. That means this implies limit n goes to infinity, expectation of xn same as expectation of x. Okay, so you need some dominated function or the random variable y where y is integrable functions. Okay, so in particular, if you have say some xn is a bounded sequence of random variables such that xn converges to x, okay, then I can always apply this dominated convergence theorem. Basically, you don't need there. It says that bounded convergence theorem. So if xn, that is why the bounded convergence theorem is a special case of dominated convergence theorem. Because xn is bounded, so xn is less than or equal to m for all m. Now, since it is a constant, it is integrable, we know, is it not? So it is independent of any n. So it is hence it is integrable. So m belongs to L1 of omega, and hence I can interchange the limit and integration. So this is called the bounded convergence theorem, and as I told that bounded convergence theorem is a special case of dominated convergence theorem. Okay, and also we'll prove it so-called the Fatou's lemma. Okay, you heard about all these things in your major theory class. Since you are all MSc students, so you know major theory class and so on. Not only that, even I think in your probability class also you have seen this kind of convergence theorem. Okay, so if not, actually just go back and then look at these three important theorems called dominated convergence theorem, monotone convergence theorem, bounded convergence theorem, Fatou's lemma. These are the three main important theorems we will apply in many places. Okay, so these things, it says that we have proved our elementary renewal theorem. What it says that limit t goes to infinity, mt by t is equal to 1 by mu, where mu is the mean of ti, or the expected value of ti, where ti is the entire arrival times. Okay, yeah, I'll stop now, and then next day I'll talk about the proof of Walsh theorem, and then the central limit theorem for renewal process. We know the central limit theorem for the sequence, so here also we try to find out the central limit theorem for renewal process, and then the many important theorems about renewal process and their applications, how to use the theorems in a real life problems and so on. Okay, in particular we will look at so-called the age of a renewal process, and then the residual life, the total life, and their distributions and so on. Actually we'll look for. Okay, so basically the residual life means basically suppose at time point t you have a renewal, and then for the next renewal you are waiting. So then what is the waiting interval? That is called the residual life, and then using the renewals theorem and so on, we'll look for the distributions of this residual life, then the total life, and then the age of a renewal process and so on. We'll denote it. So all these things actually we'll use it, means we'll study in this chapter called the renewal process. Okay, and then there is a concept called the delay renewal process, stationary renewal process, and where we are applying there, is there any physical motivations for that or not, and so on. Okay, so I'll stop here. If you have any question, please let me know.